Hey, this is Brock Lemires, and we're continuing our study of embedded systems design by looking at timers. In this video, we are going to look at how to create a signal which is called a pulse width modulated waveform. And we are going to look at how you can do this on the MSP430 using timer compares. Okay, PWM, what is it? It is a super common electrical signal that you see in embedded systems. And one of the reasons it's so popular is because it can be used as a control signal. And so one of the most common things that you use a PWM for is controlling motors. And so if you've ever heard of like a servo motor or a continuous motion servo motor or even a DC motor, one of the things they do is you tell the motor when to spin and which way to spin based upon a PWM signal, okay? And let's first define what a PWM signal is, and then we'll talk about how it's used to control. Okay, so first and foremost, it's a periodic signal, which means it repeats, okay, so it has a period. Okay, so you have the period of that, and that basically, period is always defined as like edge to like edge. So it's either the rising edge to rising edge or the falling edge to falling edge, but it is an amount of time that represents one cycle of the PWM signal. Then you have the on time, and the on time means the amount of that period, which is a 1, and then the rest of the period is a 0, okay? And so then what you do is you define this thing called the duty cycle, which is basically the on time divided by the period, and it's a percentage. And so if you think about a perfect square wave, it has a 50% duty cycle. So it's on half the time, off half the time. But PWM signals tend to be smaller than 50%. Otherwise, it'd just be called a square wave. And so if you had something, this one we're looking at right here is probably something like a 20% PWM. And so it's 20% on, 80% off, 20% on, 80% off. And so that when you define something, somebody will come up to you and say, well, I have a PWM signal. And you go, oh, great. And you got to ask, what's the period and what's the duty cycle? And from that, you then know how to sketch out what its waveform looks like. The reason these are used as control signals, it's very interesting because with one signal, what'll happen is like a motor, you can actually have a PWM period, or excuse me, duty cycle that you send to the motor, and that tells it to stay still. And then what happens is as you like widen the PWM period, it'll start spinning like maybe to the left. And then if you shrink it, it'll spin to the right. And so it's just a control signal. And you can also use these when you want to like turn things on and off. So an LED is a classic example. So you'd want to turn an LED on. Well, it turns out you don't need to drive the LED 100% of the time with a logic 1. You can actually like turn it on and then turn it off or stop driving it, and the light will continue to come out because of the capacitance of the LED. So you can actually get it to the point where it looks like it's on and you don't have to drive it continuously, and that allows you to save power. Or you can actually use it to dim an LED. So you can get these little these little duty cycles smaller and smaller where the LED looks like it's turning off slowly. And so you can create dimmers. That same concept of only turning things on for a little bit of the time is also how you can control DC motors. So DC motors is if you give it a voltage, it just starts spinning as fast as it can. But then what you do is that the way you slow it down is you say, I'm going to give you a little bit of voltage and turn you off, a little bit of voltage and turn you off. And that way you can actually slow it down. So very popular signal, very, very common. And we can implement those with timer compares. And so the whole idea here is we have two independent timing events that are related to each other. One of them is a period, and you can obviously figure out that we could use a timer compare to generate a period because we've done that before. But now we are at the point where we have something we want to do that could actually benefit from having two compares occur. And so we use two compare registers, one to generate the period and one to generate when you transition to set the duty cycle. So let's look at how this would work. Let's say, for example, I'm trying to generate this duty cycle right here. And you set up a counter, and the first thing we want to do is we want to set the period. Well, the period is ideal to be controlled by a CCR0. Remember, CCR0 is a value that represents the highest count that the timer will get to before it rolls over and goes back to 0. So, okay, that's great. We can set the period of a PWM signal using CCR0. And then how do you do the duty cycle. Well, consider this. What if every time you rolled over at the value of CCR0, you set the output to a 1, okay? So that would represent you're at a 1 when you start this thing. What if you then had another compare at a time that represented the number of counts for the duty cycle you want, and when that event occurred, you take the signal to a 0. So you would start at a 1, and then a compare would happen. You put it to a 0, and then it sits there for the rest of the period, and then a compare happens. You go back to a 1, then you go along, another compare happens, you go to a 0, and then you go, you let the whole period go, then you go back to a 1. Well, you can do this with 2 compare registers. You use CCR0 to set the period, and its interrupt service routine will basically say, please take the signal and go to a 1. And then you set up another compare, and in this example we use CCR1, and its job is when it fires, it will take the signal to a 0. So you have 2 separate compares that are altering the same signal. You have 2 totally separate interrupt service routines that are actually modifying this. And that's perfectly legal, okay? That's perfectly legal. Okay, so let's do an example. Let's flash LED 1 with a 5% duty cycle. So first of all, we will create a period of the PWM that's 1 second. And then we are only gonna have this on for 5%. Now that is pretty small. That's actually only 50 milliseconds, but it's fast enough, or I guess it's slow enough is what you should say, is that you'll be able to see it. It's just gonna look like this flash little bleep. There's a beep, 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 and it's gonna repeat every second. Now, if I made this like 0.1%, I probably wouldn't be able to see it, but 5% is a value where it's super, super fast, but you can still see it, and it proves to ourselves that we're doing a PWM, because sometimes if you did like a 40% and you're trying to look at it on an LED, you'd be like, I don't know, that kind of looks like 50% to me. So it's like, we're gonna make this obvious that we're doing a PWM. Okay, so let's do some calculations. Let's use a clock because we're using time values that are, relatively slow. They're measured in seconds. And so we're going to have a period that's 1 second. So if I do my calculation of the time elapsed is always equal to the period of the clock times the number of counts, I can put in the time I want, which is 1 second. I can put in the period of the clock, which is known, 1/32K, and then I calculate the number of counts. In this case, it actually comes out to be 32,768. That's kind of nice. But that's the number of counts that if I put that into CCR0 and the timer's in up mode, it will roll over, generate a flag on CCR0, and then continue forever. So that will be my periodic event, and that CCR0 interrupt service routine will take the signal that I'm driving to a 1. Then I need another compare, which is going to generate the duty cycle. So what is the duty cycle? Well, it's 5% of a second. So if I multiply that, I end up getting 50 milliseconds or 0.05 seconds. So if I come over here and do a second calculation, I say, I want an event that occurs every 50 milliseconds, that occurs 50 milliseconds long. And I want the period to be off of the 32K clock, and I want to find the number of counts it is. So this is, the counts comes out to be 1638, so 1,638. So now this is really cool because remember, compare register 1, if I put this in here, 1638, and I start counting at 0, it will fire and raise a flag when the counter equals 1638. It fires an interrupt service routine, and you go ahead and take the signal to 0. But remember that compare register 1 doesn't roll the counter back to 0. It just lets the counter keep going. And so that in that way, you're allowing it to go all the way up to the value in CCR0, because only CCR0 has a special capability that it can roll the counter back over. CCR0 has special function. Whatever this value is, if you're in up, it will roll the counter back to 0. CCR1 doesn't do that. It just raises a flag when the timer happens to be equal to that, and then the timer just keeps going. So that's how we can use these 2 compares to generate a awesome. So let's look at our setup. Let's use timer B0 because we like it. And we're going to leave the timer in 16-bit mode. We got to put it in up. We will select A clock as the source. We will leave the dividers as 1. And then we got to configure some stuff. We want to use CCR0. We want to put 32,768 in there, and that will define the 1 second period of the wave of the signal we're driving to the LED. And then in CCR1, we want to put 1638 because then that's going to set the duty cycle. And then remember, the interrupt service routine associated with CCR0 is going to set the LED to a 1, and then the interrupt service routine associated with CCR1 is going to set the LED to a 0. Now, where are these interrupts? Luckily, these are 2 totally separate vectors. CCR0 is int43, and that's nice because we get to write 2 interrupt service routines, one for this guy, and we get a totally separate interrupt service routine for CCR1, which is at int42. So we are about to do a program that has 2 interrupt service routines for the first time. Okay, let's do it. So let's go ahead and fire up CCS, and let's get a little something going here. So file new and CCS project. Say, hey, how you doing? We come down in here. We're still in assembly. We're still doing a timer. And we are going to do compare. Why not? And we're going to do CCR1 and CCR0 and then PWM. Okay, somewhat descriptive. I go ahead and fire that, buddy. And now I'm ready. So I'm going to fly here. All right, so I got my main looper. First and foremost, let's get that LED ready. So it is going to be, let's do this, setup LED. Okay, I'm going to come down here. I need to do a bit set.b 8-bit operation because the ports are 8 bits if you call them port 1 through 6. And what I need to do is set, set port 1 bit 0 to make LED 1 to make output, okay, and that's LED 1. Okay, so I set that, and then what I need to do is let's set its initial value to what? Remember, this is different because we are going to generate a wave where we want it to start at a 1. So when we start, this LED 1 needs to be at a 1. So we are actually going to set LED 1 to begin. That's our initial state. And then when the CCR1 fires, we'll clear it, and then when CCR0 fires, we'll set it. So that's different than what we've done before. We need to do its initial value at a 1. That's cool. Okay, so then we're going to set LED 1 initiality. Okay, now let's turn on the old digital I/O system by clearing the lock LPM 5-bit in the PM5 control 0 register. So then turn on digital I/O. Okay. So there's that, bit G, not sure what that is. So we'll go, what? There we go, there we go. All right, now let's do setup timer B0. All right, first and foremost, we've got to clear. Remember, when you do the timer, the recommended programming steps are clear the timer system by writing a 1 to TP clear. So if I come back here, I'm going to go bit set, and now I'm doing 16-bit operations because I'm messing with configuration registers. Which are 16-bit. So I'm going to do TBCLR, and that comes from the header file. And then this is going to be in the TB0 CTL. Okay, so that clears timer B0. Timber B0. And then let's go ahead and choose the clock. So I'm going to do bit set.w, and I'm going to use this mask, TBSSEL underscore a clock. And that again is in the TB0 CTL register. So this is going to be choose a clock as source. All right, and then I do bset.w, and I need to put it into up mode. Remember, CCR0 doesn't have its function, or only has its functionality, its special functionality in up mode. And that special functionality is its ability to set the highest value of the counter before it rolls over. So very important. Put in up mode. All right, so let's check spelling. Spelling. Looks pretty good. All right, ready to do this? Now it's time. Setup compares. All right. First and foremost, I need to move .w a number 32,768 into TB0CCR0. Okay, so I'm going to go CCR0 equals 32,768. Pretty self-explanatory, but remember, TB0, CCR0, that is the register that holds the value for CCR0, the register 0, that will basically, when the timer equals that value, it'll roll it over. Okay? Okay, nice. All right, let's do the CCR1 value. So move.w, and I'm gonna go pound 1638, and that's now gonna be in TB0CCR1. So this is a different register. This is 16,638. Okay, remember that one is this guy. So I just put that into TB0CCR1. Okay, all right, life is good. That's the compares, right? So now let's do some setups, some interrupts. So that's all I needed to do for the interrupts. So now, or for the compares. So let's set up the IRQs. So check this out. I'm gonna do bit set.w, and I'm gonna do pound CCIE in the TB0CCTL0 register. So local enable, local IRQ enable for CCR0. Okay, think about what just happened. CCIE is a bit mask, and we're going into the timer B0, and that's the capture control register for 0, for CCR0. So now that's just CCR0. But now what I'm going to do is, while I'm here, I'm going to clear the flag. Love clearing this flag. So I'm going to do CCIFG, and that's going to be in TB0CCTL0. So now I'm going to clear CCR0 flag. Okay, that's pretty cool. Now check this out. I'm going to copy and paste. So I'm going to copy and paste this. Okay, and when I did that, I want to now do the exact same thing, local enable, but I want to do it now for CCR1. Okay, so what changes? The bit masks are identical. That can be used across multiple configuration registers, but the control register is now for CCR1. So see how that worked? Nice. All right, let's do some, let's turn on maskable interrupts by doing EINT. So this is global enable. All right, you ready? Everything's set up. Let's do this. Main, and do a stupid loop, jump main. All right, we got a whole lot of stuff going. Now it's time to do our interrupt service routines. So let's do this. Bada boo. And we can actually do some copy and paste here too if we want. So ISRs. Let's do our first one. Let's do CCR. I don't know. What do you want to do? CCR1 or CCR0? It don't matter. They'll both be almost identical. ISR underscore TB0 underscore CCR1. Okay, so this is going to be the one that flips it down to a 0. Okay, so what do I do when I get in this interrupt service routine? Remember what we're trying to accomplish. We're trying to do this. When CCR1 fires, I want to take LED1 to a 0. That's my whole point. So I need to do a bit clear on bit 0 at P1 out. Okay, so LED1 equals 0. Now what else do I need to do? I got to clear my flag, and I got to remember I'm in CCR1 here. So I got to make sure that when I come up here, I'm grabbing the right one. And this gets confusing because there's a lot of different values in here, but a lot of different numbers, and the register names look very similar. So anyway, I clear CCIF in the TB0 CCTL1, and I am feeling great. So RETI. All right, check this out. I'm going to copy and paste this. And now I want to do the interrupt service routine for CCR0. What is my goal when I run this interrupt service routine? It is to set the LED. That's all I'm going to do. So I'm going to come in here and I'm going to change the name. And instead I go set bit 0 P1 out. So now LED is going to be 1. But now what I want to do is I need to clear the flag in the TB0 CCTL0 register. All right, so we almost got it, but we need to set up a couple vectors. So let's go down here. First and foremost, let's do this one right here. Oh, make sure these are against the left here. Okay, so I'm gonna grab that and put it on the clipboard. Okay, I'm come down here and I'm ready to do a little vector tabling. And so here we go. I'm going to do dot sect and who we want to do first. Well, let's go remind ourselves where these are. So int 43 is for CCR0. Okay. All right. So let's do that one first. Int 43, and this is for CCR0 vector. Okay. And then in there, I'm going to do a dot short, and I'm going to go put the interrupt service routine name for this guy. Okay. And now what I want to do is do the next vector, which is dot sect, and it's dot int 42 is for CCR1. So I go dot int 42, and that is CCR1 vector. And now I do dot short, and I do ISR TB0, and this is CCR1. All right, that's it. Let's see what kind of typos we have on here. So we'll fire this buddy up. We are letting it run. Exists. No, we got an error in here. No big deal. Let's go see what it was. Okay, so I come down here in my console, and I'm looking for where the error is, and it's saying it doesn't know what TBSSEL is. Well, no kidding, it doesn't, because I only put one underscore in there. So when I set this up, I need to do boom. Save that up, no big deal. Go ahead and compile it again. This time it looks like it's feeling a lot better. All right, that's feeling good, feeling good. All right, now it's on there. Got my board plugged in here, and we should be able to see this LED 1. So here's LED 1 right here, okay? And I'm ready to run this thing. Here we go. Ready? Yes, look at this. So look at that little flash. 5% of the time. That's 50 milliseconds, okay? 50 milliseconds. And now you think, like, I want to see if the period is right. So as soon as it hits, I'm going to go. Look at that. So the period is 1 second, and it's flashing 5%. Now that's 50 milliseconds. You're like, I can't even believe I can see that. What's actually happening is you drive that LED, and it's got a little capacitance in it, so it stays on probably longer than 50 milliseconds. But the signal that we are driving to it is indeed 5%. Absolutely. Wow. We just did a whole lot of stuff. We set up a pulse width modulated signal with a predefined duty cycle and period. We used 2 separate compare interrupts to pull it off. Wow, that was awesome. Nice work. All right, that's it. As always, remember to support my channel by subscribing, and see you.